Good morning, madam. So I'll start off with the introduction. But what is gas chromatography? So it is basically an analytical technique that is applicable to gas, liquid, and solid samples. So it is one of the most sensitive and widely used techniques for the separation and analysis of mixtures of volatile organic compounds and semi-volatile organic compounds. So there are three main system components in the GC system. So first is the sample injection unit, second is the column, and third is the detector. Sample injection unit hits the liquid sample and vaporizes it. Moving on to the column used to separate each compound, and the detector detects the compound and outputs their concentration as electrical signals. So then the principle of gas chromatography. So the components in the mixture are distributed between two phases, stationary phase and mobile phase. Mobile phase is also known as a carrier gas, which carries the mixture through the stationary phase. So compounds in the mobile phase interact with the stationary phase as they pass through. So when a mixed solution sample is injected into the GC system, the compounds contained in the sample, including the solvent components, are heated and vaporized within the sample injection unit. After that, the target components that were vaporized in the sample injection unit, they will be transported by the carrier gas to the column, which is a stationary phase. So once in the column, the mixture of the compounds is separated into various components, and the amount of each component is then measured by the detector. The detector then converts the amount of each compound into an electrical signal, which then sends these signals to a data processing unit, and the data obtained enables the determination of the type of compound that was in the sample and how much of the compound were found. So therefore, under the same driving force, the retention time of different components differs in the column, thus moving out of the column in different orders. Next, the question that we are discussing for this PBL is to suggest a technique to overcome the issues of the normal GC, which is it cannot accommodate samples with high boiling points and extreme polarity. So we are going to suggest a technique that can overcome these issues so that it can achieve good separation of analytes with high boiling point and extreme polarity. So the article that we chose is titled Compositional Analysis of Heavy Petroleum Distillates by Comprehensive 2D GC, Field Ionization and High Resolution Mass Spectrometry. So the summary of this article, it states that recent progresses of combining comprehensive two-dimensional GC separation, field ionization, and the time of flight mass spectrometry for the detailed analysis of vacuum gas oil distillation cuts. So a new data analysis strategy is implemented for the compositional analysis, and using this approach, a total of 16 hydrocarbon types and 14 sulfur types and their carbon number distributions were determined in the 3 VGO cuts using the 2D GC technique. So that is what we are going to discuss about in our presentation. That's all from me. Thank you.
For the instrumentation part, based on the article stated that the machine used is known as Agilent 7890 gas chromatography with a flame ionization vector, or commonly known as FID, and a split or splitless inlet system. So this two-dimensional capillary column system is a combination of a low polarity first column and a mid polarity second column thermal regulation ensemble installed between these two columns. In this article, the effluent of GC, short form for gas chromatography, with GC is split into these two streams, one connecting to the FID and the other connecting to the ion source of the Joule MS through the transfer line. So in the image there, you can see there is an Agilent 7890 gas chromatography machine that is actually used in the article itself. So the sample that is used in this article is the crude oil with a few nominal boiling points. The first being 650 to 702 Fahrenheit, second 702 to 752 Fahrenheit, and lastly 752 to 777 Fahrenheit. So the methodology actually begins with a 0.2 microliter sample that was actually injected with a ratio of 50 to 1 split at 300 and 300 Celsius in a constant flow mode of 2.010 ml per minute helium. So the oven was programmed from 45 to 315 Celsius at a 3 Celsius per minute for a total run time of 90 minutes. The hot jet is then kept at 120 Celsius above the oven temperature and kept constant at 390 Celsius. So then the MS transfer line and the ion source were set at 350 Celsius and 150 Celsius respectively. So the modulation period would be actually run for 10 seconds.
Okay, I'm Kai now discuss about 2D GCFID and 2D GCFIT or FMS image. The second dimension separation is dominated by the aromatic ring types. The higher the aromatic ring classes, the longer the second rotation time. As boiling point of the class increase, the 2D GC image move toward the upper right and become broader, indicating the increase in molecular size, variety, and composition complexity. Vacuum gas oils VGOs molecule erupt very closely in the 2D GC space, making it difficult to resolve individually components by 2D GC FID only. The second ionization mass spectrometric help to resolve the overlaps and greatly improve the resolution of petroleum compounds. The 2D GC TOF MS image become narrow as boiling points increase. Now this is how to divide the 2D GC MS data by nominal mass classes, and the calculation for nominal classes is shown below. The chemical formula of petroleum molecules is CnH2n plus ZX. Okay. Here is the recognition of petroleum chemicals by Catrix max defects analysis. KMD procs of the 600 to 702 degrees Fahrenheit cut where KMDs are brought against nominal classes for the 7th nominal mass classes. Each nominal mass classes box contains multiple homologous series. For example, in the Z equal to 2 box, there are 3 homologous with KMD varies around negative 9, 13, 80, and 173 respectively. About 19 homologous in total can be recognized. The inset in the right bottom corner is rated the KMD distribution of the 3 homologous in the Z equal to 2 box. The peak waves indicate the spread of the KMD values. The delta KMD at full waves at half maximum is about plus minus 10 KMD unit. In this world, a KMD window of plus minus 20 KMD unit is used to select max peaks for the further 2D GC analysis. The general chemical formula of the petroleum CnH2n plus ZX is assigned. And this is now we discuss about the full composition analysis by combining 2D GC and KMD window selection. Two-dimensional gas chromatography 2D GC separation was conducted for the nominal mass class separation. At KMD of 40 plus minus 20, general chemical formula CnH2n minus 6 was assigned. At KMD of 130 plus minus 20, exogenous terrace 3-ring aromatics and benzoin terrace furnace 2 rings aromatic were observed. In KMD of 220 plus minus 20, diterase phenol benzene minus 14 2s was used. The same approach was repeated for all nominal mass classes to resolve petroleum types. About 30 plus molecular types were recognized, and they were divided into hydrocarbon type and sulfur carbon types. Exact decreased molecules become more unsaturated and erode progressively later in the second dimensional GC separation. Starting from Z equal to negative 10, both sulfur and hydrocarbon molecule were observed. Sulfur molecule always erode early in the second dimensional because they are more saturated than their isobaric hydrocarbon counterparts. And this is the table for the composition of vacuum gas oils distillation casks. A total of 16 hydrocarbons type and 14 sulfur type were listed and compared for the 3 boiling point casks. Hydrocarbon type range from paraffin 1 to 3 rings cyclic paraffin and 1 to 4 ring aromatics. Sulfur combined in group 1 to 3 ring cyclic sulfurics and 1 to 3 ring aromatic trivalents. The relative concentration of sulfur compounds and contains aromatic species increase with boiling point and the cask aspects. The figure shows that the molecular width distribution of Z equal to -4 and -6 hydrocarbon class in the 650 to 702 degree Fahrenheit cut. Top is non-biomarkers molecule, bottom is biomarkers molecule. The mass distribution of biomarkers molecules is really smooth. For the petroleum distillation cut, the distribution shifts toward the right side as boiling point of the cask increase. The carbon numbers peak at C21, C22, and C23 for the 3 boiling points cutter respectively. The mass distribution of the biomarkers molecule bottom part are very spiky, indicating the favorable skeleton structure retained for their biological precursors. The code skeletons tricyclic and tetracyclic structures start with the carbon numbers 19. Tricyclic biomarkers distribution peak around C21, C23, C24, C28, and C29 respectively, while the tetracyclic sterins peak around C21, C22, C27, and C29 respectively. Abundant C19, C21, and C22 sterins were also observed. So from this article, it really showed that the combination of GC can solve the main problem of the GC can use to observe the detail of the analyze which have the high boiling point and extreme polarity. It can show the detail in graph and image from the combination of the GC. That's all from me. Thank you.
Hi, madam. So I will be talking about the comparison between normal GC and 2D GC combined with MS and FI. So for normal, basically it separates petroleum molecules by combination of boiling point polarity, while the combined, the FI generates molecule ions only mass spectra, and the MS allows accurate mass analysis of hydrocarbon molecules. And the normal, basically, petroleum analysis is basically limited to the samples with nominal boiling point below 1000 Fahrenheit or around 537 degrees Celsius, while the combined use soft ionization such as field ionization and single photon ionization to minimize fragmentation, which has been explored and successfully used in petroleum analysis. So as for the conclusion, basically the combination of 2D gas chromatography, separation, soft ionization, and high-resolution mass spectrometry greatly enhance compositional analysis of heavy petroleums. And by nominal mass class separation, selective Kendrick mass defects, KMD window, and 2-dimensional gas chromatography, 2DGC separation, 30+ petroleum homologous series will fully resolve. Even the difficult-to-resolve mass overlaps were separated clearly. And the sulfate and aromatic sulfur compositions are hard to separate from hydrocarbon signals in the 1-dimensional gas chromatography and time of flight mass spectrometry, 1DGC TOF-MS analysis. And finally, 2 series of biological markers were also revealed with unique carbon number distributions. That is all from us. Thank you very much.